OSPF is one of the most widely used routing protocols. It uses several complex terms and concepts. This video simplifies these terms and concepts for learning and teaching. Unlike traditional routing protocols, OSPF does not share routing information blindly. It limits the routing information exchanged between routers. It shares only what is necessary and required for routing. It first builds a neighborship and then shares routing information only with neighbors. For example, this network has 4 routers. If you implement a traditional routing protocol such as RIP, all routers will share all routing information with everyone as soon as you enable it on all routers. However, if you configure OSPF, routers will not share any routing information until they establish neighbor relationships. To build a neighborship, they go through several steps and use many components. Let us understand these steps and components in detail. OSPF allows you to run multiple instances on the same router. Each instance is called a process. Every process is unique and does not share routing information with other processes running on the same router. A process is locally significant. You can use the same process ID on the different routers. However, you cannot use the same process ID to run 2 processes on the same router. Running multiple OSPF processes on the same router provides no benefit if you want it to share all routing information with other OSPF routers. It is beneficial only when you want the router to share specific routing information with other OSPF routers. Let us take an example. In this network, OSPF is running on these routers. You want to configure OSPF on this router. How you will configure OSPF on this router depends on how you want this network to function. If you want this network to work as a single network, configure only one OSPF process on this router and advertise all routes in that process. If you want to divide it into 2 separate networks, configure 2 OSPF processes and advertise only relative routes in each process. If you use this configuration, routers running in Network 1 will not learn about the routes and routers available in Network 2. Similarly, routers in Network 2 will never be aware of the routes and routers available in Network 1. However, this router knows routes and routers available in both networks. This configuration allows the router to connect to different OSPF networks without mixing their routing information. You can use it in a situation where you want to connect multiple OSPF networks separately using a single router. OSPF processes are locally significant. You can use the same process ID on the different routers. You cannot use the same process ID to run 2 processes on the same router. Each OSPF process runs as an individual OSPF instance. Each OSPF process maintains separate routing information. It does not share its routing information with the OSPF process running on the same router. Running multiple OSPF processes on the same router is beneficial only when you want it to connect to other OSPF routers separately. If you want to share all routing information, use a single OSPF process. It will make OSPF configuration straightforward. When you start an OSPF running router or enable an OSPF process, it checks for the existing router ID. Router ID is the unique identity of a router in the OSPF network. If a router ID is present, it initiates the OSPF process. If not, it first selects the router ID and then uses it to start the OSPF process. If it fails to pick a router ID, it does not begin the OSPF process. It uses the following steps to select a router ID. It checks the running configuration to find the manually configured OSPF router ID. You can configure a custom router ID using the router ID command in OSPF configuration mode. If the router finds a custom OSPF router ID, it uses that and does not check the next option. If it does not find a custom router ID, it uses loopback interfaces as an alternative. If a loopback interface has an IP configuration and the interface status is up, the router uses its IP address as the OSPF router ID. If multiple loopback interfaces are up and have an IP configuration, it selects the loopback interface with the highest numeric IP address and uses it as the OSPF router ID. If no loopback interface exists or all loopback interfaces with an IP configuration are down, the router uses the third option. It picks the highest IP address on its active interfaces and uses it as the OSPF router ID. Unlike the first and second options, the third option does not provide a fixed router ID. If the interface whose IP address is selected as the router ID goes down or receives a new IP configuration, the router reassigns the router ID. Since it does not provide a fixed router ID, you should not use this option. If it fails to pick a router ID, it does not begin the OSPF process. Let us see how it works on a router. You can use any network simulator software, such as Packet Tracer, GNS3, or a real router for practice. No matter what you choose, the commands and configuration steps are the same on all platforms. Add a router to the workspace of your network simulator software or connect to a physical router and open a console connection. Right now, this router has no OSPF configuration. You can use the Show IP OSPF command in privileged mode to verify it. If the manually configured router ID is not available, it picks the highest IP address configured on the active interfaces. Use the Show IP interface brief command to view the IP configuration and state of all interfaces. Right now, this router has no active interfaces. On it, configure 3 OSPF processes. For 3 OSPF processes, it needs 3 OSPF router IDs. Unless it finds a valid router ID, it does not start the OSPF process. To verify it, create the first OSPF process. The router OSPF command in global configuration mode creates a new OSPF process and enters OSPF configuration mode. It accepts a process ID as an argument. Since a router ID is not available, it does not start the process. Use the router ID command to assign a manual router ID to the first OSPF process. It attaches this ID to this process and starts it. Exit this process. For the second OSPF process, create a loopback interface, assign an IP address, and start it. OSPF will automatically pick it as the router ID for the second process. Create the second process. Since an active loopback interface with the IP configuration is present, it uses its IP address to start the OSPF process. For the third process, access any physical interface available on the router, assign an IP address, and start it. OSPF will use it as the router ID for the third process. Create the third process. It uses the IP address of the physical interface to initiate this process. To verify that the router uses these IDs to start OSPF processes, run the Show IP OSPF command again. As the output verifies, the router used the IP address of the physical interface to start the third OSPF process, the IP address of the loopback interface to start the second process, and the manually configured router ID to start the first process. OSPF uses areas to provide scalability. An area is a group of contiguous networks. OSPF uses it to control when and how much routing information is shared across the network. Traditional distance vector routing protocols use a flat network design. A flat network design causes scalability issues in large networks. It also reduces the overall network performance. If a change occurs on one router, it affects every router in the entire network. If the network has only a few routers, the effect is negligible. However, if the network has many routers, it can bring the entire network to a halt. Let us take an example. A network has many routers. In this network, a link is flapping. Flapping links cause the connected routers to update their topology tables and to inform the other routers of the change. Connected routers update their topology tables and inform their neighbors. This process continues until all routers learn the change. This process occurs whenever the link goes down or comes up. A flapping link triggers this process so rapidly that the routers fail to reach convergence. A flapping link causing trigger updates is not only the problem the flat network design has. Apart from this, it also has many other issues. Let us understand them. In a flat network design, each router must learn and store information about all other routers, including their IP addresses and routes. Each router needs to maintain and process an extensive database. A larger database requires more memory and CPU cycles. OSPF uses this database to compare and select the shortest path for every destination. It requires processing power that grows exponentially compared to the size of the topology database. Managing and troubleshooting a flat network is also challenging. If something goes wrong, you have to check the entire network. To overcome the limitation of the flat network design, OSPF uses a hierarchical network design. It breaks the topology database into several smaller databases using OSPF areas. With areas, it places each link into one area. Each router runs its routing algorithm only on its area topology. It does not need to learn the routes outside the area. It only needs to know the routes within the area. However, it needs to learn a summary of all routes available outside the area. For example, in this network, these routers only need to learn links 1, 2, 3, and 4. They do not need to know links 10, 11, 12, and 13. Similarly, these routers do not need to learn links 1, 2, 3, and 4. However, these routers need to maintain the summarized routes available in each other's area. OSPF supports a two-layer hierarchy, the backbone and the areas connected to it. The backbone area is compulsory. It represents the OSPF network's top-level hierarchy. It uses the number 0. Apart from area 0, all other areas are known as non-backbone or areas connected to the backbone. All other areas must have a link to area 0. All areas inject routing information into the backbone area. The backbone area broadcasts that information into all non-backbone areas. A backbone router has all interfaces in the backbone area. An area border router is a router with interfaces in both backbone and non-backbone areas. An internal router has all interfaces in a non-backbone area. It has the fewest responsibilities in the OSPF network. It maintains only area-specific routing information. An intra-area route is a route to a subnet inside the same area. An inter-area route is a route to a subnet outside the area. On an Ethernet network, OSPF uses a client-server architecture to share routing information. In this design, a router called DR acts as a server. The server is responsible for keeping and providing updated routing information. If a client has updated routing information, it shares that with the server. The server updates its database and shares that with other clients. Since the DR plays a lead role in how the database exchange process works, OSPF implements an additional router as a backup for the server. This router is called BDR. A BDR maintains the same routing information as the DR. If the DR fails, it immediately becomes the DR. It acts as a hot standby for DR. Apart from the DR and BDR, all remaining routers are considered clients. They are known as DR others. A DR other router talks to a DR using the multicast address 224.0.0.6. The DR and the BDR talk to all other OSPF routers using the 224.0.0.5 multicast address. An LSA is a data packet that contains routing information in a format that OSPF running routers understand. It describes a specific part of the OSPF network. OSPF running routers use it to exchange routing information. They maintain a database known as the LSDB to track all exchanged LSAs. An LSDB is a collection of all LSA packets the router knows. LSA flooding is a process that OSPF routers use to share and learn all required LSAs. During this process, all routers collectively advertise all known LSAs to one another. At the end of this process, every router on the network has all the required LSAs. Convergence is the state in which all OSPF routers are aware of all LSAs. After convergence, if any information changes, the affected router creates an LSA describing the change and floods the LSA into the network. Each recipient validates the LSA update and sends an acknowledgement back to the sending router, confirming receipt of the flooded update. There are 11 types of LSA. OSPF routers use each LSA type to exchange different information. From these types, types 1, 2, and 3 are essential. An LSA Type 1 message is known as a router LSA. OSPF routers use LSA Type 1 messages to advertise their router ID and information about directly connected networks. LSA Type 1 messages do not cross the area boundary. They remain within the area. An LSA Type 2 message is known as a network LSA. In an Ethernet broadcast environment, DR uses LSA Type 2 messages to share the routing information with the other routers. LSA Type 2 messages also do not cross the area boundary. They stay within the area. An LSA Type 3 message is known as the summary LSA. ABR routers use LSA Type 3 messages to exchange routing information with the other ABR routers. That's all for this video. In this video, I explained the basics of OSPF. In the upcoming video, I will explain the OSPF algorithm and configuration. If you have comments or suggestions about this video, please share them in the comment section.